Hi everyone, welcome back to Chem Story. Today we're starting Chapter 9, and we're going to talk all about ethers. We'll look at how they bond, what their shape looks like, and why they're polar. We'll also go over how ethers are classified, including subtypes like epoxides and cyclic ethers. And toward the end, we'll wrap up with their physical properties and how they're used, especially as solvents. Alright, let's jump in. So let's start with the basics. What exactly is an ether? An ether is an organic molecule where an oxygen atom is bonded to two carbon groups. These carbon groups can be alkyl, like methyl or ethyl, or aryl, like a phenyl ring. The general structure looks like this: ROR', where R and R' are the two organic parts. One way to think about it is this. Take a water molecule, H2O, and replace both hydrogens with carbon chains. What you end up with is an ether. Simple as that. Now let's take a closer look at the structure. The oxygen in an ether is sp3 hybridized, just like in water or alcohols. That means it has 4 electron groups around it, 2 bonding pairs and 2 lone pairs. So the electron geometry is tetrahedral, but since we only see the atoms, the actual shape looks bent. The bond angle? It's usually around 112 degrees, a bit wider than the ideal tetrahedral angle. Now let's talk about how ethers are classified. One simple way is by looking at the 2 carbon groups attached to the oxygen. If they're the same, like 2 ethyl groups, we call it a symmetrical ether. But if they're different, like 1 methyl and 1 propyl, it's called an unsymmetrical ether. Here's another important type: cyclic ethers. These are ethers where the oxygen atom is part of a ring structure, and one key example is an epoxide, also known as oxirane. It's a 3-membered ring with an oxygen in it. And because the bond angles are so tight, around 60 degrees, there's a lot of ring strain. And that strain makes epoxides a lot more reactive than regular ethers. Other cyclic ethers include oxetane, a 4-membered ring, oxalane or THF, which has 5 members, and oxane, also called THP, a 6-membered ring. Polyethers are molecules that have multiple ether linkages along a single chain. They're usually made from repeating units like CH2, CH2O, and the chain can go on and on. Sometimes, that chain even loops around to form a ring. On the left, you've got a typical linear polyether, and on the right, a cyclic version, like what you see in crown ethers. So whether they're straight or ring-shaped, polyethers are defined by those repeating ether units. Now here's where it gets even more interesting. Crown ethers don't just sit near metal cations. They actually wrap around them and trap them inside their central cavity. It's like the ether forms a little cage that holds the ion in place. This kind of interaction is called a host-guest complex, and it's a classic example of molecular recognition. The crown ether selectively binds ions based on size and charge, a powerful concept in supramolecular chemistry. Here's a good example of how crown ethers work. Each one has a different size and number of oxygen atoms, and that controls which metal ion it can bind. 12 crown 4 fits lithium ions really well. 15 crown 5 is just right for sodium, and 18 crown 6 wraps perfectly around potassium. They act like molecular cages, grabbing onto specific ions based on size. What you're looking at here isn't just a regular structure, it's an electron density map of actual crown ether cation complexes. On the left, 18 crown 6 is forming a complex with a potassium ion. On the right, 12 crown 4 is wrapped around a lithium ion. The colored surfaces show where the electrons are, and you can clearly see how the oxygen atoms are interacting with the ion at the center. The cation fits snugly inside the crown ether's cavity, perfectly held in place by the surrounding lone pairs on oxygen. It's a textbook case of host-guest recognition, and this kind of image makes that normally invisible interaction easy to see. Now let's shift gears and talk about some physical properties of ethers, starting with polarity. Ethers are actually polar molecules. That's because oxygen is more electronegative than carbon, and it also has 2 lone pairs of electrons. So the oxygen side ends up with a partial negative charge, delta minus, and the carbon atoms attached to it are a bit positive, delta plus. This kind of polarity affects how ethers interact with other molecules, especially through intermolecular forces. Now here's something important to keep in mind. Even though ethers are polar, they don't have any acidic hydrogen atoms. So unlike water or alcohols, they can't form hydrogen bonds with each other. But the lone pairs on oxygen can still accept hydrogen bonds from other molecules, like water or alcohols. That means ethers can act as hydrogen bond acceptors, but not donors. So between ether molecules, the main force is dipole-dipole interaction, weaker than hydrogen bonding, but stronger than just dispersion forces. Let's talk about boiling points for a second. If you compare ethers to hydrocarbons of similar size, ethers usually boil a little higher. That's because ethers are polar, so they have dipole-dipole interactions, something hydrocarbons don't have. Take propane, for example. Its boiling point is around -42 degrees Celsius. Now look at dimethyl ether. It boils at about -25 degrees Celsius. Still low, but clearly higher. And that's thanks to those dipole-dipole forces. But if you check out ethanol, it's way higher, around 78 degrees Celsius, because it can form hydrogen bonds, which ethers can't. Here's another clear trend. As the alkyl groups get bigger, the boiling point goes up. That's because longer carbon chains mean more surface area, which leads to stronger London dispersion forces. For example, dimethyl ether boils at -25 degrees Celsius, diethyl ether goes up to about 35 degrees Celsius, and dipropyl ether jumps all the way to 91 degrees Celsius. So more carbons means more molecular weight, more surface area, and a higher boiling point. Pretty straightforward. Ethers aren't just interesting structures, they're also really useful solvents in organic reactions. Why's that? First, they can dissolve a wide range of organic and inorganic compounds. Second, they're chemically stable, so they don't react easily with other reagents. And third, they usually have a low boiling point, which means you can easily remove them after the reaction by just evaporating. That's why ethers are commonly used with things like Grignard reagents, organolithium compounds, and even strong bases like sodium hydride or sodium amide. Here are some common ether solvents you'll probably run into. First, there's diethyl ether, the classic example, especially in intro-level organic chemistry. Then we have tetrahydrofuran, or THF, a 5-membered cyclic ether that's actually one of the most widely used solvents in real lab settings. It's polar, super versatile, and works well with lots of different reagents. You'll also see 1,2-dimethoxyethane and 1,4-dioxane. Both are useful ether solvents, each with their own strengths depending on the reaction. But what ties them all together is that same basic structure, an oxygen atom connecting 2 carbon groups. And that wraps up our introduction to ethers, their structure, types, and physical properties. They might seem simple, but they play a big role in organic chemistry, especially as versatile and reliable solvents. Thanks for watching, and I'll see you in the next Chem Story lesson.